Okay, so the topic today is Ising meets Fibonacci. So to get into my story, let me first give you a bit of history, which is when Ising met Fibonacci. Here's Ising, Ernst Ising, father of the Ising model. Here's Fibonacci, Leonardo of Pisa, son of Bonacci, so that's why he got his name. Now you would think, these people, there's some 800 years in between, so you would think they never ever met, of course. But in fact, they did meet. It's a kind of little known fact in history. Somewhere in the 1700s or so, some neutral spot, I think it was in Geneva. They actually talked to each other. They talked in English, amazingly. And this little conversation, which I'll show in a second, is actually quite revealing. Leonardo of Pisa was a very smart guy. This is well known. But he was way ahead of his time, as you will see from this little dialogue. So he says, Leonardo of Pisa, my onions are better than yours. And Ising gets a bit annoyed. He says, you solved my model in 2 dimensions. He says, Fibonacci, that'll be easy. How about 3 dimensions? And then Ising gets annoyed and the conversation ends here. So you see, Fibonacci was about ahead of his time. He was apparently thinking about problems for quantum computation. He could solve the Ising model and whatnot. Okay, so much for history. Today I'd like to have the 2 gentlemen meet in the sense of their respective anions getting together on a quantum Hall interface. So my story for today is the following. I'm going to imagine a 2-fluid quantum Hall system with the red and the blue part. The left part will support Fibonacci anions, and I'll explain in quite some detail what my system is and how this comes about. The blue part will support these Ising anions, and the issue will be sort of most of what my talk is all about is what happens in this interface, where there's this kind of mismatch of 2 different types of non-abelian anions, and this interface has to somehow reconcile these 2 things, and something happens there, and we'd like to discuss how that goes. So this analysis was in the recent paper with Eta and Rostel, who I'd like to acknowledge for this collaboration. So I have a certain way of bringing this story. There are different approaches. Already yesterday we had the talk by Simon, which was about rather similar matters, although a different way of getting around them. So I'll try to emphasize the way we did this and what goes into it. Actually, what goes into is very little. That's, I think, the beauty of the analysis. You'll have these 2 quantum Hall states, which will be Moore-Reed, MR, and non-abelian spin singlet. And they're completely nailed, in a sense, by just one property. So, they're longer level quantum Hall states, etc. But there's one thing that singles them out from everybody else, and that's this pairing property. And in the simplest form, which would be for the bosonic version of these states, it's simply this here. We'll have a property of the many-body wave function for lots of these boson particles, that the wave function survives when 2 particles come to the same position. So it doesn't become 0, but it does become 0 if more than 2 come to the same position. Okay, so this is a form of pairing. You can put particles on one spot, but you cannot put more than 2 on one spot. So it's paired, but it's not clustered, so to say. Now this thing alone singles out, as I said, special states. So if it's for spin polarized electrons, this will be the Moore-Reed state. For unpolarized, it will be this other state, this non-abelian spin singlet state. And somehow having this sort of space singled out with this pairing property, we also have sort of built in this interface situation, because it also becomes a part of the space where this condition is met for all particles involved. So somehow by zooming in onto this space, which I'll do in quite some detail, we can pretty much for free read off what this interface will look like and what it will do. And that's actually quite pleasing. So the analysis is, in the end, very simple if you follow all the steps carefully. Okay, to implement this pairing property, we often think of a Hamiltonian that penalizes, violations of the pairing. So there's this delta times delta interaction, so to say. So it becomes non-zero if 3 particles come to the same spot. And so if you don't want that, as we will insist on, you actually insist on the 0 energy property for this interaction here. So we'll have the lowest number level situation, and then we'll put this interaction, which simply kills everybody that doesn't go along with the pairing property. And also, to do things in the computer, this is very convenient if you do it this way. You generate all the right states and you eliminate all the rest. And again, so my whole story for today, for the Moore-Reed and the NAS phase and their interface, will be to rely only this and to make progress from this starting point only. Okay, so let's start with the easiest of the two states, the Moore-Reed state, and let me go through some of the properties, again emphasizing how they relate to this pairing property. Well, first thing, the Moore-Reed wave function, its bosonic form would be like this. So this you must have seen before. Is this Jastrow vector with a Pfaffian in front, and you can see that this makes zeros for every pair of coordinates. The Pfaffian can take out zeros, but never 3 at a time, so to say. So this wave function has this pairing property. And if you have the general Moore-Reed wave function with this m parameter sitting there would be gotten by taking this bosonic wave function, which is symmetric, and multiplying an extra factor z minus e to the m. So if m is half, that's fermionic wave functions. If you take m equal to 1, that would be the 1/2 state, which we think is related to the 5/2 quantum Hall effect. So again, you've seen this before, I think. Now, second thing, there's another way to write very easily a wave function that has all the right properties, which is what Nicolas Regnault calls the colorful expression. So the idea is that you essentially write Laughlin wave functions for sets of coordinates, but you make two groups, or two colors if you wish. So in the first group you have half of the z's and they make this Laughlin wave function. The second group, the rest of the z's, they make a Laughlin wave function with exponent 2. It's a bosonic thing, and now you see, if you have this and you symmetrize over everybody to make a true bosonic wave function, you easily have this property, because if two particles come together, more than two, sorry, then they have to be two in the same group, and then they make a zero within that group. So this is a very easy way to enforce this very same property, and if you count powers of z between this previous expression and this one, they're the same, so these have to be the same expressions, and you can indeed show that this is an identity, these two things are the same polynomial by all the z's. And sometimes it pays, or it's easier to think in this logic of enforcing the pairing condition rather than with this Pfaffian, especially if you go to the spin singlet case where the Pfaffian isn't available, and this formula pretty much carries over, and you can easily use it. So that's two expressions for bulk wave functions. Now, I'll have to bring up conformal field theory. And one way to do that is to sort of be, very highbrow and say this is topological field theory, and it comes from Chern-Simons, and there's all kinds of ways these things come together. So there's 2 + 1 dimensional topological field theory. There's an edge that carries 1 + 1 dimensional CFT. The bulk comes from a 2 + 0 dimensional CFT. But another way to actually bring this in is much more down to earth, which is to say, well, we want wave functions with the right pairing property, and conformal field theory can do this for us. And so you don't even have to know all these other sort of connections. You can simply pursue this program of identifying the right type of paired wave functions and using CFT just for that purpose. So the way you use this as follows: you make wave functions by taking correlators of a suitable operator and a suitable CFT. So that's the psi sub electron. You compensate with a background charge, and this correlator is going to be your wave function essentially. And you see, if you follow this prescription, you can look for an expression of psi electron which is such that this pairing property actually happens. And here is how you do this. So you put this bosonic vertex operator, which makes a 0 between every 2 of them, and then you put this psi which makes this pole between every 2 of them, and then you can see again that from only these 2 properties, whatever comes out as a wave function from this correlator is going to have the pairing property, and of course this is going to be the Pfaffian wave function by construction. A bit obvious, but in the other example that comes later, this is not so obvious anymore. So again, the CFT, if you understand your fields and your operator products, it gives you a tool to actually construct these paired quantum Hall wave functions. Now the CFT does more. If you have this ground state identified, you can easily, the CFT is particularly suited as a language to identify excitations. So what you do is, within the CFT, you look for other operators, which are the quasi-Hall or quasi-particle fields, and you make them such that they don't kill the condensates, so that they don't make cuts in the condensates. So you insist on this property with integer exponent, and if you identify these phi's, you can make wave functions in the presence of a bunch of these phi's inserted, by inserting literally in the correlator these phi fields at your favorite location, W1, W2, etc. And in this way, you build new wave functions which still have the pairing property, but which now have these defects built into their structure. So in the case of the Moore-Reed state, this is the electron operator again.
And the nicest quasi-hole, the smallest of them all, the smallest charge would be this one. So you take half a charge, in this case, this is the bosonic Moore-Reed, and you put this sigma field coming from the Ising quantum field theory. And since there's a half power between psi and sigma, and there's a half power between this and that charge operator, the whole thing is local with the compensate, and you make the famous charge half excitation, which would be the E over 4 excitation if you think about the nucleus half fermionics thing. Okay, so this way you see that this full Ising CFT comes into the story, the psi electron for the electron part of the wave function, and the sigmas that are coming with the quasi-Hall insertions. And so you have the whole package, and this whole CFT is behind the quantum Hall situation. So knowing this, you can actually make progress and continue. For example, you can look at the juicy bit, which is, for example, the non-abelian statistics part. So that starts happening if you have at least 4 of these insertions of a quasi-Hall. So let's say those are 4 sigmas. Then, because of the fusion rule down here, there are 2 channels to choose from. So there are 2 independent wave functions for quasi-Halls. So you can, compute this thing by just wrapping up this correlator. So Merck and Wilczek did that quite long ago. And you find 2 independent terms. There's an A term with a certain ZW structure, B term, and both have 2 channel versions. So there's channel 0 and channel 1. And that's all explicitly available. These formulas can be found in their paper. And having those formulas, you can start braiding the W's around each other, and you can inspect, explicitly without any advanced formalism what this braiding does to you, and you discover then that braiding the W's mixes the 2 channels with certain matrix operations, and you have this famous situation of non-abelian anyons, and because of the whole story, these are then the Ising anyons. Okay, so this is building up that story, and again, I think most of you haven't heard much news so far, but I'll follow the same logic for this other state and then for the interface, and maybe those are new things for some of you. Okay, so now this was sort of the bulk situation. 2D plane, I didn't bother about boundaries or about spherical geometry. It turns out it pays, as often in quantum Hall, to go to the sphere and do your bookkeeping there. Because on the sphere everything becomes a finite dimensional problem, and it's actually a nice way to get your hands on the interesting properties, particularly in the end, the interface properties. So here's how quantum Hall in the sphere is done. This goes back to Duncan Haldane. Very early on in the quantum Hall history. So you use the fact that on the sphere there's a nice SO3 for angular momentum. So the Landau levels form orbits of with fixed LZ values. So the top orbit, let's say the North Pole, would be the minus n5 over 2 if there's n5 fluxes. Then there's the plus n5 over 2 down there. So the whole thing has a good angular momentum structure, which is very convenient in analyzing things. And if your quantum Hall wave function sets at filling factor nu, you have to adjust this right amount of flux to actually allow that state to come to life. So there's this relation, the number of fluxes is 1 over nu number of particles minus a small shift. And so this gives a setting, in a sense, the one particle kinematics are like here. And if you add this interaction that I insisted on, the delta-delta interaction, you can simply ask your computer or sit down and do it by hand what the many-body states are. And you can, for example, zoom in on these Moore-Reed states, for an example. So if you go for the bosonic Moore-Reed state, it turns out the number of fluxes you need is n minus 2, because the filling is 1 for the bosonic Moore-Reed. The shift is 2. So if you fix the number of fluxes to be n minus 2 for n particles, there's a unique ground state, unique zero energy state for this interaction, which is the Moore-Reed state. Has angular momentum 0, so it's just the perfect Moore-Reed state on the sphere in a five-dimensional setting. Now, what I'll need for the rest of my story is actually not just the Moore-Reed state itself, but I need to study these the degeneracies that arise if you add extra fluxes, which means if you insert quasi-Halls in various places. And I'll, in the end, rely on counting formulas that tell you exactly how many states become possible if you put extra fluxes. Now, to get into that story, I'm not sure if I should actually stop to have you do an exercise, but here's a way to actually get you into the story. I'd like you to follow some of the details of these formulas because they are the juice of the analysis. So here's a little exercise. Suppose you have 4 particles. So let me write this here. So we do bosonic Moore-Reed, okay? We take 4 particles. That makes it simple. So if let's do the wave function. That's well. So what's your favorite version? The Faffian or the other one? The other one. Okay. So here's the formula. So we have 4 of these particles. So we make 2 groups. Let's say we have 1 and 2 sit in one group. Z1 minus Z2 squared. That's the love limb of group 1. Then the product of 3 and 4. Well, notation isn't quite careful, but you get the idea. There's this thing here, and then you symmetrize over all 1, 2, 3, 4 to make the truly bosonic wave function. So I think that's correct. Yes. So the total degree is 4, and you see if you take one of the z's alone, for example Z1, you'll see the thing runs from Z1 to the 0, it uses Z1 to the 1, it uses Z1 to the 2. And so what is available is you put n phi flux is actually Z1 to the 0 all the way to Z1 to the n phi. That's the maximal orbit that's available. So you can see that to get this right, you need n phi equal to 2, which is precisely n minus 2. So that's the number of particles minus the shift. So that's the ground state, and that's the unique thing. If you only give 2 fluxes, which means you only allow the z up to power 2, you get a unique way to get zero energy for the delta-delta interaction, and that's it. Now, so what I want to do now is actually give the system a little bit more room to position its electrons by adding an extra flux. So I put a delta n phi equals 1. So n phi becomes now 3, which means I'm going to allow z to the 0 all the way to z to the 3. Okay, so I can actually build extra wave function because I can give myself an extra factor of z1 or z2 or whatever, and still try to find combinations that that have the pairing property all right. Okay, so that's a little game of how you discover the possibilities that you have here. So let me actually give you the way this is nicely done. If you start from this expression for the, let's say, the wave function without any excitations, the idea to do is that if you put, okay, let me put it this way. So you put an extra flux here, which means that since the nu is equal to 1, you allow yourself a quasi-whole charge of 1, filling times extra flux. But since the basic quasi-particle charge is a half for the bosonic mobility, you get 2 units of quasi-particles instead of quasi-whole. So you get, let's say, 2 locations where you can actually put a quasi-whole, if this would be the infinite plane. And what you can try to do is to write the wave function now as the original, let's say, the ground state wave function, which is over there, but now with insertions of, let's say, in the first group you put the W, so the 2 first Z's, they meet this W1, and this, the 2 other Z's, they would meet the other location of the other quasi-hole. You see, if it's a Loveland state, you want to insert a quasi-hole, what you do is, you put a factor of Z minus W for all the Z's meeting all the W's, so to say. But this is a paired states, it's a bit different. What you can do is, you sort of split the flux insertion to 2 locations. In the first location, you meet half the Z's, the other you meet the rest of the Z's, and then if you symmetrize, you're still in your zero energy space, and everything is just fine. So these are the kind of expressions you can write. And now if you look at kind of a basis of what these things are, you can look at the various expressions in the W's that generate relevant Z polynomials. So for example, you can extract from this whole expression the part that multiplies W1 to the 0, W2 to the 0. And that would be a good quasi-whole wave function. And then you can see what you have. So you can do, so this would be just 1. You can do W1 plus W2 multiplying a piece. You can do W1, W2, which is symmetric. You can do W1 squared plus W2 squared. You can do W1 squared W2 plus W1 W2 squared. And you can do both of them squared. Okay, so there are 6 independent Z polynomials with all the right properties, and they all fit within this space. If you look at the way I did this, I made sure none of my Z powers was going to exceed what I allowed, namely 3. Okay, so in the end, this is going to give 6 possible steps, and that's my answer. And if you keep track of the LZ, so the powers of the Z, so the individual level orbitals, you'll find, well, let me actually write it here. So you find the whole partition sum Z of Q is going to be Q to the minus 2, and then there's this Q polynomial 1 plus Q plus 2Q squared plus Q3 plus Q4. And so these 6 terms are one along with these 6 choices made over here. So if you wish, you see 6 states, and you see from the structure here, 1 plus Q, etc. to the 4th, that's going to be L equals 2, 5 states of L equal to 2, and then the one remaining state will be L equal to 0 multiplied of angular momentum. Okay?
So I guess the essence of this trick is that because of, well, you get these functions from inserting quasi-holes, but inserting quasi-holes preserves the property that the electrons still have this, well, if the two come in the same place, it doesn't have to be 0.
Yes, that's my game. So the game is, everything I write on the spherical geometry and also other geometries has to live in this constrained space which has the pairing property. And that will include my interface, which is the final end of the talk. And all I do is, if I allow myself the minimal amount of flux, I can just make the movie state and that's it. If I make more room by putting extra flux, I can make more things. And I'm freeing up extra Hilbert space. And you see the way you count this is the example that will be more that I don't do on the blackboard. But the thing is, if you think of it, you can actually sit down and do it and discover the rules. And you see the interesting feature. For example, if you have 4 particles on a sphere, and if it's just London or so, and you insert a single flux, you get an L equals 2 multiple. You get 5 states, W to the 0 to W to the 4, and that's it. And here you see, because there's this breaking up into 2 separate pieces of quasi-hole, you get more. There's already an extra contribution L equals 0. And the whole thing is, if you put more fluxes, you get way more, much more. And you get this interesting structure of the quasi-hole Hilbert space. Okay, so here is, let's see. Yeah, so here's this thing written out in a bit nicer, but that's on the blackboard. So you see, here's the way you write W insertions in this colorful expression, and then you start counting what you have. You have to be, in the W's you go up to W to the 2, and you're symmetric, so you get these 6 ways, and you can write a little partition sum. Now, next step, this has been all figured quite long ago by Nick Reed and Ed Rezai, actually not in this colorful formalism, but in the other one using that Pfaffian wave function. So here's the result for this partition sum in closed form. If you do, just delta n phi with any number of them. So if you do delta n phi flux insertion on top of mu read, you create 2 times that much quasi-holes, because one quasi-hole needs half flux only. And you can do this exercise that I did here, but now for the general case. And there's a nice closed form expression for what that gives you, which is this expression here, where it's a Q polynomial, but a funny one. So it's built from Q binomials, which are animals like this, where these Q sub A things are like that. So if you put Q to 1, this is just counting, and you get the usual combinatorial factors. But since we like to keep track of the Q dependence, because that's the LZ, that's the angular momentum structure, we keep all these Q expressions, and the compact way of collecting the whole result would be this here. So if you zoom into n equal to 4 here, that's going to be this little expression over here. But now it's a big one that involves a big summation. Now, actually, I should have maybe put a few more arrows on this expression. There's kind of 2 reasons why these numbers grow as fast as they do. And I guess you all know what they are. The first is that if I showed that if you put more than 2 quasi-holes, let's say 4 or 6 or 8 or so, there's all these ways to choose your fusion channel. Okay. And in the end, that pretty much sits in this factor here. For example, if you forget about the second factor and you simply sum over this combinatorial thing, you get 2 to the n over 2. And that's the number of fusion channels if you put n of these quasi-holes. The second reason there's all these degeneracies is the fact that these quasi-holes sit in spherical geometry, so they have places to go. So there's orbits available to the quasi-holes on the sphere, and you can place them in many ways. And there's some counting involved into that. So if you're on the plane, you can pick your W positions sharply. If you're on the sphere, you cannot do it sharp because you're in a finite dimensional space. But you can put these things in orbitals, and there's again choices going with that. And so the whole thing combined gives you this expression. And again, I'd like to stress I can derive this, it's a bit of work, but you can derive this just starting from the pairing property, lowest lambda level sphere, and you just do it and you find this result. Even if you don't know conformal field theory, if you're brave enough, you can do this and find the result. Now, one way to use this, and that's getting into my logic for today, is the following.
Can you back up just? So, well, I actually assume F has the same parity as N.
Yeah. I didn't put that.
So I sort of, when I see these formulas, I always think, F fermions and N over 2 orbitals and N minus F bosons and N orbitals or something like that. Do I see how that is translated immediately into this partition sum? I mean, it looks like the exact same expression.
Yeah, for example,
is there an easy understanding?
For example, if you summarize my little example here, in the end, the counting that goes here is I have these W's, they have 3 orbitals, 1 W squared, and you have to put 2 of the W's in a symmetric fashion. That's what you do here. And that's this factor. So this factor tells you put n quasi-nulls in a certain number of available orbitals. And the other factor is the fact that this fusion rule degeneracies. So, yeah. And so if you wish, this F, I guess, is the number of unpaired electrons in the terminology of Reed and Lazai. That's how they identified their F. So if you start doing quasi-nulls, you can yes or no break these Pfaffian pairs, and the number of times you do that is this F.
But I guess the question is, why is it that translates from, usually it's just a usual binomial coefficient, and that tells you the total number of states, and here it's now a Q binomial coefficient. Why is it that, how did that happen?
Well, it's sort of a cute thing. You see, the counting comes in you know you're going to end up with good multiplets like the momentum. So you get these complete, series of 1 plus Q plus and the way, the way that they come out of the counting is you get it right in one strike if you replace the binomials by their Q deformed expression. Which is quite cute, because from the conformal field theory side, these Q theories are all over the place. But they're not coming from spherical geometry. They're from a different source, so to say.
But so if I just took a simple boson problem, the binomial counting of states, the partition sum becomes a Q binomial. That's sort of a generic property.
Yeah.
Okay.
Yeah. So actually, well, there will be this formula for the null states in a bit, which is much more difficult. And with Eddie, we derived this sort of using a lot of conformal field theory inside, because we couldn't do it the straight way. Okay, so let's see. I was making the following point now. What I'm after, in the end, I keep announcing my story, is a two-fluid situation. Now, to practice a bit how we can do that, we're going to do the following. We're going to take Moore Reed with an edge. So we start on the sphere, but now I'm going to make a hole in the sphere, and that will make an edge between the hole and the liquid, and I can look at the edge between those two things. And now the way I do this is I use my counting formula, and I simply imagine that I put lots of these quasi-holes. So I make my small n large, and I imagine putting them all, let's say, close to the North Pole, and I'm just going to make a microscopic hole where all these quasi-holes are pushing out all the particles. Okay. And if you think about it, you see what my partition sum here does, it summarizes every possible way to put the n quasi-particles. And among those is the possibility to put them all near the North Pole. Okay, so one of the terms in there, the term with the lowest Q power, so to say, would be just that. And all the rest of the terms are then fluctuations on top of that situation. Okay, so if you think for a bit, this is what we call the giant hole technique. If you simply take this n very large, the interpretation of the counting formula changes from a sphere partition sum of quasi-holes to actually an edge character separating the hole from the liquid. And the way this works is quite beautiful. So I take my counting formula, without any modification. I take lots of particles and lots of quasi-holes to make an actual microscopic hole, and I simply see what I get. And my formula simplifies to this Q expression, which is a well-known thing. So it's a boson partition sum 1 over Q infinity, and the rest of it is this expression here, which you can rewrite like this, and which is just a Majorana fermion and conformal field theory character. Okay. So this here tells me that I should expect this partition sum for an edge between Moore Reed and vacuum. Now, of course, this is not a new thing. There was an analysis quite long ago by Xiaogang Wen, who did exactly this. So he didn't do my sphere story and all the characters. He took open geometry, so he took it this. He put this exact three-body Hamiltonian, because he knew all the pairing and everything, and he did it on the computer. So he generated, you know, a spectrum with, I think, 8 particles. He looked at, and you see, this is the spectrum. The picture is a bit bad, but you can hopefully see it. And you see there's all these states above here, and then there's zero energy states down here, which are sharp zero energy because they have this pairing property. And you know, Xiaogang generates multiplicities. So there's 1 at the lowest m, which is some number like this, and there's another 1, and then there's 3, 5, 10, etc. And those numbers they collected to a Q series like this, which is exactly the same Q series I had on my previous slide. Okay. And obviously, because of the whole consistency of the whole framework, these Jakob von der field theory characters, because these edge things in the end can be described by the von der field theory. But even if you wouldn't know that, you know, if you would know this expression by counting all the things that I counted for you, you could derive this thing without any further input. Okay, so I guess you're slowly starting to see how I'm going to pull this interface off. So this is a little funny technique to get these things on the table.
So, yeah, where did you put in that all the closed particles are placed at the top of the sphere?
Well, in a sense, you know, in the, well, let's see. So in the Q expansion of this expression, it's the leading state, so to say. So this is a big sum, let's say like this here. So in a sense, this is the one with the lowest Q power, which means all the particles are maximally down on the sphere. The final term would be the opposite. All the particles are near the other pole. But what I interpret is that you see, I'm sort of thinking from this term on. This is the term where the hole sits near the North Pole. And the first so many terms here are fluctuations on top of that situation, where this interface starts wiggling a bit. And you know, one of the particles actually, you know, moves up a bit into the hole, and you get an edge excitation. And if you go all the way, you know, you accumulate all possible edge excitations, you can actually reverse the hole to the other side. But if you only think the first so many terms, you're really thinking of the hole with fluctuations around it.
Okay, but so you're not actually cutting off the series or anything, you take this limit from
yeah, and actually in doing this limiting procedure, you kind of break this symmetry, so to say, and you only look at the hole in one place plus excitations around it. Because if you make the two ends large, you're kind of losing sight of the opposite possibility, which is higher in the spectrum, so to say.
Is there an order of limit, small, large n to infinity for small n class or something like that?
Not even, I think. This, well, let's see. Yeah, I guess the small n is going, the large n goes fastest to infinity. That's what I want. Okay, so I hope this is all right, because what's coming will be variations on the same theme. Okay, a few more things to round off my more read part. So, one more thing that's important to complete the physical picture, something I'll refer to later, is the fact that there's bulk and there's edge, and actually there's this possible contact between the two. So if there's, for example, 2 guys in the bulk in a certain fusion channel, that has an effect on the edge spectrum. And if you imagine tunneling in an excitation from the edge into the bulk, changing the fusion pattern, that also changes the edge structure. And I'll refer to this in the end of the talk, so I'd just like to mention this. This is one thing we studied with, again, Aton, Roosevelt, and Adi Sturm, Rudy Ila, in some recent work. So putting it all together, this is sort of my summary of the Moore-Reed situation. So there's the blue liquid with the pairing correlations, the bulk excitation are the easing anions, along the edges are these neutral edge modes, the Majorana fermions, and the charge mode. And you know, you can relax a fusion channel situation in the inside if you can tunnel in these psi modes from the outside, and thereby you can reset, so to say, the qubit or the quasi-particle fusion channel inside. So this is the complete picture for the blue part of the story. Comes the red part. So now, from now on, it's very easy. If you listen carefully, I'm going to repeat every single thing I did, but now I'm going to work with 2 types of spins. So I'm going to put spin and half electrons. So, and I'm doing the very same thing. I'm putting the same pairing interaction, you know, which is sort of a spin-less interaction. It doesn't see the difference between the 2 kinds of particles. But the problem does change, because what changes is the symmetrization business. You know, I have to insist on the bosonic wave function. And you know, it matters if you have 2 kinds of bosons, ups and downs, or if you have only one species. So in particular, if you look at, you know, the densest possible states, which would replace mu-read for the unpolarized case, you can actually pack the bosons a bit denser than you can if they're polarized, because the symmetrization is less constrained. You have two types. So, for example, the bosonic state that comes out has filling 4/3 and not 1, and the fermionic one has 4/7 and not a half. So you see, it's a slightly denser state because there's an interplay between the two types of spins. So here's an example with 4 particles, 2 ups, 2 downs. This is actually the solution, so you can see this expression, if you look a bit, it has the right property. But it's only, the total power is only 2, whereas for the spin polarized case, it's still here, the total power is 4. You see, it's only also fewer fluxes. I only need, let's say, the zeros in the first power of the individual Z's here. So I need, what is that? 1 flux and not 2 fluxes for 4 particles. So it's a different story, different filling, everything different, but the same pairing correlation is built in from the start. Okay, so if you start studying these wave functions, the colorful expression is still available with appropriate modifications. The Pfaffian expression is not, because there's no easy way to write these factors in this case. And what's very helpful again is the Coulomb field theory to generate the wave functions. Now, if you study this, you identify quickly what you need. You need the SU3 level 2 CFT, which has two abelian directions, one for spin, one for charge, and then there's a parafermion bit. So the central charge is 16/5, one for charge, one for spin, and then the rest is parafermions, which replace the Ising fermion for this new situation. These come with central charge 6/5, so they're interacting fermions in this sense. I'll show them in a second. There's 2 guys, so one for spin up, one for spin down, and then there's all these quasi-holes. We had a sigma for each, and now we have a bunch of sigmas, which are different fields in the parafermion CFT. And for example, if you do the 4/7 state, the fermionic state, there will be quasi-holes which are spinless but have charge 2/7, and there will be spin-half quasi-holes with charge 1/7, and each of them has their own sigma to insert into the condensate. Now, here is what these parafermions look like, and it's a kind of a funny structure. You see, if you only have psi1, it behaves like a Majorana fermion. This OPE is just that. If you only have psi2, it's the same thing. It's just Majorana. But the new thing and the complication is that if psi1 meets psi2, it's a non-trivial combination. You actually generate a 3rd fermion that's part of the structure. Okay. So this actually suggests, if you think of it, that the way to think about this non-abelian spin signet state, it's paired all right, but in a sense, it's built of quadruples of particles. Because, to get actually into the one channel in all possible ways with 4 particles, you would need 2 psi1s and 2 psi2s. Okay. So the way we think about this state often is as it builds from groups of 4 particles, which form a spin signet and the paired thing combined. And those things condense and they build a condensate. So that's the parafermions, and again, they're harder to work with because of this complication. You cannot do Rig theorem and write correlations because this makes it much more complicated. And then the spin fields, there's these 3 sigmas. There's also a thing called rho, and they have their own structure, which is a bit complicated. But you see, sigma plus sigma gives 1 plus rho in all kinds of ways, and there's a lot of structure in that theory. And there's also, conformal dimensions which are different from what you have seen. This is a half like for Ising. These are different numbers than for Ising, a 10th and 3/5. Details are not so important for our story here. I do like to mention one thing. You see there's this field called rho here. It's actually 2 fields. For the experts, SU3 has 8 dimensions. There's always 6 coming from the roots and 2 coming from the middle center of the hexagon. Those are the 2 rows if you look through the whole structure. And it matters in the end. So I'll just mention here there's 2 of these rows with their own separate structure. And toward the end I'll have a point where this matters, and you should remember this little thing. Okay, now an important thing. All these OPEs are complicated, but if you do the following, if you group the 1 and the psi's, you call them, let's say, 1, and everybody else, the sigmas in the row, you call, let's say, phi, and you look at how they fuse, how the OPEs work, it's very simple. 1 is 1 is 1, 1 phi phi, and phi times phi is 1 plus phi. That's if you coarse grain these fusion rules. And now this looks, I guess, familiar. These are the Ising fusion rules. Right? Sorry, the Fibonacci fusion rules. This is different from the Ising case, because here, for Ising there was sigma is 1 plus psi. Now there's only one extra sex of phi, and it sort of fuses to itself or to the identity. And so because of this little thing, you should expect that the phi quanta, which are the sigmas, which are the quasi-holes of the Nasse state, should be these Fibonacci anyons and not the Ising anyons. So that's the quick argument. The actual check that this is the truth of the matter is a bit hard work. So here's an analysis I did with Eddie a few years ago. We actually computed 4-point functions of quasi-holes. So here's the case with 4 times the sigma 3, so the neutral quasi-hole. And just to check this Fibonacci aspect, we sat down and computed these things explicitly. So it's a correlator in this CFT. There's a whole lot of factors floating around. Some of it was available from old work of Knishi Samochikov, but the combination of sigmas and psi's in one correlator was a new thing, so we worked on that. And there's a whole talk of how we did that. But in the end, there's a formula which is similar to the Nayak-Wilczek formula for the Ising case, but different in the details. So there's coefficients A and B's which hide F's, and F's are hypergeometric functions. So there's a lot of structure, but in the end, this is explicit and it allows you to check things about braiding. So for example, if you take this guy and we know the 4 W positions, we can actually break them and just read off from this expression what happens, and use all kinds of things about these hypergeometric functions. And you discover certain matrices acting on the fusion index upon braiding. So this is one of them. If you do all 3 of them, this is the result. Braiding 1 and 2 gives this here, 2 and 3 gives that, 3 and 1 gives that. And this is the familiar, the celebrated set of braiding matrices for the Fibonacci anyons, which I think one of the first papers about this was Joost with Sander Weiss, who got at this from a very, very different perspective, using quantum groups and things like that. But this is an explicit check that, from our construction, these quasi-holes are going to be Fibonacci anyons. That's what I wanted because I wanted a second fluid which actually has the Fibonacci anyon sitting there. So in a sense, you see this. You probably know these Fibonacci anyons better from the 3rd Reed-Precise state, which is spin polarized but with clustering of order 3. So somehow these 2 cases are very similar. So Reed-Precise 3 is SU2 level 3, and we are SU3 level 2, and these things are very similar mathematically. There's level rank duality. So it's not so surprising that the braiding structure comes out almost identical. The only difference, if you look at the details between Reed-Precise and us, would be these kind of prefactors, the abelian prefactors to the non-abelian matrices. All the rest is identical. And it has to be because of CFT consistency conditions. Okay. Okay, so now I need to go to my next step, which is this counting business on the sphere, because that will in the end give me access to my interface. Here's another exercise which I'm not going to do on the blackboard. You could do the same exercise, let's say 4 particles, but now include the spin and work out the velocities. It's actually a nice exercise, but it will take a bit too much of my time here. Here's the result. So if you do 4 electrons, you put 1 flux, that means 4 quasi-holes, because now the fundamental quasi-particle has only a quarter of the filling for its charge. You could discover this here. So in this case, without the spin, I had an electron still equals 0. In this case, I should keep track of spin, which is a good quantum number all through the story. And you discover if you put 4 quasi-holes, you can actually fully polarize the system. So you find more Reed as an excited state in the background of the Nasse state, and you find other stuff as well. And you find 20 states already, so it grows much faster than it does for the polarized fields. Yes?
You have 3 different quasi-holes. Do you consider one of these quasi-holes, or you consider all possible combinations?
Everything that would fit within the Barry constraint is taken along. So this is, so you can even do the analysis without sort of committing yourself to how you name the quasi-particles, because you're just seeing which polymers in the Z have all the right properties and fit within the maximum power that you allow yourself. Okay, so you can do this analysis. You can do a bigger case. So here's, if you do 8 electrons with 8 quasi-holes, so that's also only that's actually 2 extra fluxes. So this was actually done by Ed Zai on his computer quite long ago. And while he did that, Eddie and I worked on an analytic analysis of the same story, and in the end we had a happy agreement. So we had a formula, and he had this numerics, and it all agreed. And the formula is here. So this is quite a nice expression, which summarizes the whole thing. So now we pick our favorite number of up and down electrons, favorite number of up and down quasi-holes, do all this, and we count and we count and we count, and we find this partition sum on the sphere. So that replaces this retrovalue result for the polarized case. And again, these little tables that I just showed are special cases. If you take small numbers, you can work out the explicit details. So that's available. That's a nice result, I think. And now you can use it for going to edges. So first application is, let's make a hole in the NAS state. Okay, same idea that I had before. So I take everybody large, and up and down, and the two type of quasi-holes. And so actually, coming back to your question, Maria, that you see the N3, or the third type actually missing from this analysis. And I think the point is that you can always make that by fusing an up and a down together. And it's a matter of taste, I guess, if you give that a separate identity, so that's a different type of quasi-hole, or if you view it as a composite of an up and a down quasi-hole in their signet channel. Okay, so now here you see making this hole what it does. So here's the expression on the sphere, and here's the reduction that you get if you make this hole and you interpret what you get as an edge partition sum. And what you see is this whole expression becomes two bosonic factors, so that's the spin and the charge modes on this edge. And then you find a funny result down here, and this is actually a known result from the CFT literature. Kunipa et al. It's precisely the vacuum character for this quaternion theory here. So you discover again that without even knowing all the CFT lingo, if you have this expression available by doing your counting right, you simply read off the edge structure without any further ado. Now, to be honest, the way we derived this formula, we knew about this here, and in part we worked backwards to actually get our hands on this expression here. But for my presentation today, you could follow the logic of reading it this way. Okay, so summarizing the red states, the NAS, here's everything I said or almost said. So it's different liquid, Fibonaccianians in the bulk, neutral stuff at the edges is these two parafermions, the psi1 and the psi2. And there's again this notion of bulk edge tunneling that relaxes the bulk fusion channel. In this case, the rhos are doing that. So these the rho quanta, the rho S and the rho C, the two of them can actually change fusion channels if they can tunnel into the bulk and reach the quasi-hole locations. Okay, so final item, I think I'm sort of well in time for that, is the combination, which is what I was heading for all the time. And now it's only one slide to give you the result, because of all the work I did so far. Because here's the following thing. So here's again this partition sum of the NAS state on the sphere, with my favorite number of quasi-holes injected. And now what I do, I do a slight modification from the previous slide. I'm going to take a huge number of n up, of the up-type quasi-hole, but I'm not going to put any of the down-type quasi-hole. Now what that does, you see the up-type quasi-hole, they're pushing out the up-type electrons. Okay. So if I accumulate a whole bunch of the up-type quasi-hole, let's say near the North Pole, I'm going to push out all the up electrons from that region, but I'm leaving the down electrons right there. So in the end, I end up with a region near the North Pole where everybody is down electron, and it's spin polarized. And then the rest of the sphere, I still have my NAS liquid as I had it before, because I don't do this all the way, but I stop it at some partial polarization. And so what this has to give me, following the same logic that I did all the time, is this interface partition sum, this interface character. And you get it for free, so you simply do this. So you take this limit, now you keep n down 0, but you take the rest very large, and you get a different expression than before. You still find a charge mode here. The spin mode has been frozen out because I've fixed my n up and down ratio. But what you do see is a new expression giving you precisely all possible neutral excitations on this interface. Okay, which is a funny Q series. And if you look at that one, you can recognize that this is a character of a known CFT, which is a equal to 710 minimal mode from the field theory. Actually, there's famous character formulas for this CFT, and so when we got this result, we checked that they were all the same, and then we actually found in the literature, in the paper of Vivrati and Pierce, that they already had this precise formula for that character from very different reasoning that they follow. But you know, it's very nice because so suddenly, following this whole thing, you identify without further work a precise quantum field theory character that gives you precisely the structure of this interface between the two liquids. And it's kind of surprising. These are not parafermions. I mean, this is a different CFT. So here's some of the details. It has a certain number of fields with certain dimensions. They're not parafermions, but there's some kind of compromise between, you know, the one type parafermion that's liked and brought in by the mass state, and the other type that's brought in by the Murid, and they meet at this interface, and they kind of compromise on this minimal CFT for their structure. So actually, here's a little story of how you can understand these things. You know, there's many ways to understand these things. Here is if you imagine, that's actually that helps for the understanding. If you imagine separating the two liquids by a thin sliver of vacuum, you have two separate liquids, and the red one would have edge modes running, let's say, top to bottom here, which are the parafermion modes of the C6-5 theory. The other one has modes running up the other direction, which is the C=half theory. And in a sense, what happens is that these modes meet if you eliminate the vacuum strip. And what you can imagine happening is that a parafermion is gapping out. So the right moving one up here and the left moving one down there would gap out, and it would leave behind 6/5 minus 1/2, which is 7/10. So in that sense, the 7/10 is no surprise. It's simply the difference of the two central charges. And if you understand this, you can make things more precise. You can, in particular, sort of look at branching rules of fields from here, fields from there, and fields on the interface, how they combine, and how they branch, if you wish, at the interface position. And having that, which is not on my slide,
Can you back up to there's this comment, precise relation to character identity. I mean, is it something as simple as about taking characters of Ising and characters of divided by characters of parafermion, I get, or the other way around?
Pretty much. I mean, sometimes there's a sum of two terms, but it's like that, yes.
Is this in two terms? Two sectors or something?
Yeah, so I guess in certain cases a field coming in from the red side would have sort of two terms on the other side. So there's two ways for that to kind of decompose on the field in the blue state and an edge mode.
This also have to be cosec description of the 7
Yeah.
You also have sometimes you have two terms.
So I didn't prepare a slide for these branches, but I showed some pictures where you see these things in action, so to say. So let's see what is a nice one. Well, for example, here's a thing you can imagine doing. This is sort of a good experiment. If you actually I reversed the slides now. If this is the NUS side, you take one of these quasi-holes, let's say the up type quasi-hole. If you imagine putting that through this interface, it could end up as an Ising quasi-hole. But then there's a mismatch, and the mismatch actually is manifested by the fact that something runs off along this interface. And it's again as simple as pi. It's simply some of it's simply addition and subtraction. The scaling dimension of this Ising thing, the h sigma, that's the famous 1/16. On the other side, the h sigma up of the other parafermions is, I think, it's 1/10. Now the difference is 3/80, and indeed the thing running off along this interface actually has that precise scaling dimension. So in that sense, things are simply additive. The structure is actually quite nice. Now, the other thing I mentioned shortly, briefly, this fusion channel relaxation via tunneling of quanta to the edge. This is always a possibility. If you're close enough to the edge, let's say with vacuum, things like this can always happen. And in a sense, they form a leak for qubit or quantum register interpretations. Now, this interface can sort of do some of that, but not all of it, since it has some of the structure sitting on the interface, but some of it not quite. And that's actually interesting. That's where these two different rows come in. For example, you can make a qubit with 2 sigma 3s in the 4/7 bulk. And what that can do, it can tunnel a row C, and the row C, if that meets the interface, and that's one of these branching rules, it can actually run off in the form of a field that's carried by the interface and runs off like that. But if it's a row S, it cannot do that. So a row S meeting the interface has to continue in the other side, and for example relax another pair of quasi-holes on the other side, and then it leaves a little remnant on the interface. So but these two things are different. So because all the details of this OPE structure and all that, there are interesting details of what are possibilities for this interface leaking the fusion channel, yes or no. And then, well, there's other things you can imagine doing. This is actually an interesting idea to make a triple point of liquid 1, liquid 2, and vacuum, and imagine what happens there. For example, if an edge mode comes in, how does it branch between the two possible channels and things like that? We try to make some progress on that, but it seems to be rather difficult to control what's going on there. So, but again, if these things can all be stabilized, there's lots of interesting things you can imagine doing and investigating. A few more comments before I close then. One thing is that, you see, this was my version, our version of, understanding how interface between different types of nonlinear order works. Yesterday you heard Simon give another story, which actually sounds a bit like mine in the sense that it's both an issue of condensing quasi-holes, but actually the details are very different because they rely on interactions and the ground state of interactions in the many-way system. We don't do that. We're much more in a kinematical analysis. And there's also, the work of Joost Slingerland with Weiss and Hacker, which is again a different perspective, but again gives very similar results to the things we observe. So there's many ways to see these things. There's also many pretty much papers coming out at the same time. So this is happy coming together. One last thing that I'd like to mention, which is probably interesting and relevant. You see, for my story of arguing how the interface looked like, I started from this NAS state and I created the second region where it was Murid and I got the interface. If you think about if this can maybe be realized experimentally, you'd rather think in the other direction. So a possible scenario for experimental realization could be something like this here. So if you imagine that Murid is for real, the 5/2 plateau is actually a Murid phase, if you can make the Zabel splitting small enough so that the two types of spin come into the game, you can imagine increasing the filling, by just moving off center from the plateau, which would mean if you think about my spherical geometry situation, you would actually take out some fluxes. So you would eliminate some room for the particles. And as is clear from for example, the sphere story, if you insist on this pairing feature staying intact, if you take out fluxes, you have to flip some of the spins to not leave your zero-energy space. Right? So if you again imagine that it makes sense to insist on these pairing correlations also away from the Murid state, you're immediately forced to consider overturned spin situations. And then there's a number of possibilities that we don't quite know what to think. One option is that you start nucleating this NAS phase in the background of Murid. And the NAS, so all the overturned spins would kind of accumulate in spin singlet regions separated from the Murid background by this famous interface that I studied today. But another option is that, for example, the overturned spins start building skirmions, and you get a skirmion, well, liquid or lattice maybe, in the background of the Murid phase. And only if you push much farther, you in the end will find the NAS phase. You see, in the end, the NAS phase is the only option within the pairing space. But if you're only tilting a few spins by putting a few extra fluxes out, then it's unclear what happens. So we're trying to consider this issue with two of my students in Amsterdam. I know Gunnar and Nigel and also Steve consider the skirmion business from their perspective. But I think it's a very interesting issue because there's lots of room also from the experimental knowledge for overturned spins in or near the Murid state or the 5/2 state. And well, maybe these kind of ideas can help to identify what's going on there. I think this was my last slide. I do a little bit of summary. And, well, thanks for your attention.
Thank you. Further questions?
So how generic it is? Suppose I have two liquids, they have very central charge, I put them together, then this edge mode would have the new conformal field theory of the difference of the central charge? Or?
Yeah, you see, our thing is to be very specific because we've really chosen a case where the two sides of the interface share the same correlations, the same pairing correlations,
Right.
and that we create a difference by having either spin board or spin singlet. Now the construction that we heard about yesterday of Eddie and co-workers seems to be more general in the sense that it, yeah, for example, it would include cases of a number 3 with design state with a number 2 more read state, which in terms of the correlation is very different. It's you know, clustering versus pairing. So I couldn't do my story for that situation, but still they have claims on what the interface would look like. And I guess in all cases there's something going on of doing a co-set or doing a difference of conformal dimension and things like that.
So you mentioned that you might have the scenario where the 4/7 is nucleating inside the 1/2. Do you have any ideas on how you experimentally detect something like that?
Yeah, I think, you know, in tunneling across, you see that's the you see there's a bit of a analogy here with, you know, if you have the 1/3 plateau and you move off center,
Okay, yeah.
so one physical picture for that would be that, you know, you nucleate it too far with the little poles, and so you get this situation that, you know, if you're in the 1/3 thing and you move a bit to the high filling side, you know, you get little puddles of the 2/5 phase. And if you look at tunneling across, you know, you open an extra channel which is into this edge, out of the edge, and that changes, for example, the coefficients of the exponents of these dependencies. Now, in our case, it's extremely similar. So, in principle, you know, if the background is the 5/2, and then that would be the Moore state, you know, we can imagine having these 4/7s come in and manifest themselves in a similar way. But I guess, for example, if it's a Schrödinger lattice instead, you would hopefully see something different, and you would be able to tell the difference. So maybe one more, well, not maybe not evidence, but of course, it's not justifying to talk about these things at all. You see, I only mentioned one Hamiltonian today, which was this delta, which is not the real thing. So we actually we worked with this Nicolas Regnault to actually check that both these phases can actually exist, you know, as decent stable ground states of, you know, a modified Coulomb interaction. So there have been studies showing that if you modify Coulomb a little bit, you know, the Moore phase becomes pretty good. And, you know, Nicolas checked that if you also play a bit with the even coefficients of the Haldane potentials, you know, you can achieve a situation where both Moore and null are stable phases, and you can actually consider an interface at all. So.
Further questions?